So first, let me thank Torsten and Tony for the invitation, and it's great to be here, and especially like right before the 50th anniversary. So I promise what I'm going to tell you today is very simple, and basically the message is already on the first slide. But before that, let me thank my collaborators first. So this work is pretty much done with people from the Lawrence Berkeley National Lab and also University of Colorado Boulder. And Dave is here, Dave Waba is here in the audience, so correct me if I make some. So this is a picture of the Lawrence Berkeley National Lab, and this is advanced light source, which is basically a synchrotron user facility. So you can write a proposal and get beam time to carry out the experiments. And this is UC Berkeley, and this is San Francisco, it's over there, and the Golden Gate Bridge is over there. So what I'm going to show you today is how we can use basically X-ray scattering techniques to learn about the helical pitch, especially when the helical pitch is, say, shorter than 200 nanometers, when optical methods are not very useful. So right now, X-ray scattering can address a lot of a huge landscape of materials, including, say, this recently developed ferromagnetic ferrofluids, which is basically a collection of magnetic nanoflakes in solution, in solvent. Or you can study, say, for example, this metal organic frameworks, or you can study this block of polymers, polyelectrolyte membranes. So pretty much, when people ask me, like, what can you do with X-ray scattering, I always say everything, except those that doesn't work. So this is the hutch. Basically, it's a small room, and it's basically big instrument, right? So this is the sample. Usually it's over there, and then we have $1 million detector sitting over here. So and in the middle, this is a fly tube, which you pump vacuum. You want to get rid of the air because air attenuates the X-ray signal. And just show you one example. A lot of people are interested in this organic photovoltaic materials, and if you can print this OPV material on flexible substrates, it will be very desirable. So we built this complicated in situ instruments, so you can basically do in situ printing inside this hutch, and then also use X-ray to monitor the structure evolution as a function of temperature, time, when the solvents are drying, or you can say change how fast you print, or you can adjust the mixing ratios if you want to mix different, two or three different solvents into the thin film. But we also try to develop new techniques to be able to do more. And in particular, right now, the tools we have is we have typical hard X-ray scattering technique, which is the workhorse. But we also have very unique soft X-ray scattering techniques, which you can go basically from 150 eV to 1500 eV. So, which is great because if you want to look at a carbon, if you want to go to carbon absorption edge, you need about 284 EVs. So pretty much this range covers the resonant edges of carbon, nitrogen, oxygen, fluorine, and this is really fantastic for people studying organic materials because it's just all organic material is full of carbon and other material, nitrogen, for example. But also we are currently developing this tender X-ray region resonance scattering. And hopefully, we will be able to study sulfur, which is existing in many battery materials, naphthalene, thiophene, or phosphor, which is, again, in a lot of biological materials. So hopefully, in 6 months, we will be able to say, hey, we can cover pretty much 90% of the materials people are interested in. So let me tell you a little bit about liquid crystals. Why what can we do with this novel techniques? So the Banco liquid crystals is interesting because you can say if you have achiral small molecules, if you depend on how you pack it, if you want to, you can pack them into symmetric layers, which can be either chiral or racemic. And all these symmetric layers can also be either ferroelectric or anti-ferroelectric. So the point is that this is really a very interesting system which is exhibiting very rich phase behavior. And a relevant phase, it's of particular interest here is that, so this phase is basically the molecule forms these symmetric layers, and the layers are very flat. But when you cool the B2 phase down, in temperature, the layers actually does not want to stay flat. So as a result, they actually starts to twist and form these nanofilaments. So this is a typical picture a lot of people show. Basically, this is when you have crossed the polarizers, the image looks very dark. But when you decross the analyzer and polarizer, you can clearly see two type of domains, so both left-handed and right-handed. So currently, the popular model was proposed by a group in Boulder, Colorado, Noah Clark and Dave Waba et al. So, but the point is so that you have symmetric layers, and then they stack up. For example, you have 5 to 8 symmetric layers, and then they twist into a nanofilament like this. The filament diameter is about 20-30 nanometers, and then the pitch, based on TEM results, it's about 100 nanometers. So this is a TEM image. If you basically put this material into some solvents and you do the TEM again, you can see beautifully single nanofilaments. But then the question is, like, because this kind of techniques has a lot of limitations. For example, it only gives you local information, and more importantly, you're not looking at the material itself, you're looking at the replica. So it's difficult to do in situ experiments. And the measurement on the helical pitch, it's also not very precise. So what I'm going to tell you next is how we can measure the helical pitch precisely and also in situ when you change the temperature. So this has been some work done with the hard X-rays, but the success was limited because if you want to look at, say, 100 nanometer periodicity with hard X-rays, the scattering angle has to be really tiny. So this is some practical technical difficulties. And then also, if you think about it, it's basically like a piece of paper, you're twisting it. And then if you look at the electron density modulation along the helical axis, it's actually very, very small. So let me quickly show you that if you, the index of refraction, it's actually a complex number. So it's 1 minus delta and plus I beta. So beta is absorption. And when you do hard X-ray scattering, which is say 10 keV, delta is usually much better than beta. So the absorption is negligible. But when you go to, say, carbon edge, which is about here, you can see that the delta and the beta are comparable, right? So this makes a big difference when you do scattering experiments. So this is the example here. So for example, if you have polystyrene and a PMMA, and if you measure the alpha and the beta as a function of temperature, you can see that near the absorption edge, the beta and the delta can change dramatically, right? And then the intensity, the scattering contrast, actually depend on the delta square plus the beta square. So you can see that if you can basically tune the X-ray energy, and then so you can tune the contrast, scattering contrast between two materials. So this is what people typically do. You have a triblock copolymer, you have A, B, C, different segments, and then they have slightly different absorption properties, or delta and beta as a function of energy. So when you go to different energies, you actually see different lattice. So this is typically what all these polymer people, block copolymer people do. But then with liquid crystals, what we can do. So actually, when you just shoot X-ray at carbon edge through this B4 nanofilaments, you see beautiful scattering patterns at the resonance. But when you go 5 eV away, the scattering is pretty much gone, right? So obviously, this is some indication that the scattering is related to the resonant edge. Now you can do this energy dependence of the scattering intensity. So it's basically a line cut, and then you plot this in lines as a function of energy. And you can clearly see the scattering peak. This peak corresponds to the helical pitch, maximizes at the carbon edge. And then the peak intensity drops quickly when you go above the edge. So this is very exciting. But another nice thing is that with the instrument we have, we can actually tune the polarization direction. So the light here is linearly polarized. So if you have the polarization horizontal, you see the scattering intensity mostly vertical. But if you change the polarization direction, the scattering pattern basically follows. So this says that the scattering is not because of the contrast between the material and the vacuum, or between the material and some other compounds. So this is purely from the orientational sensitivity. Now let's simply assume that if you have bent core molecule like this, and say in one case the polarization is in this direction, and versus the other case, let's simply assume that there's some contrast between these two cases. Then we can explain the data pretty well. So the scattering pattern here is actually not isotropic azimuthally, right? So you have to understand why this is like that. So right now the model is that if you have say within the illuminated area, you have a combination of filaments, say vertical and horizontal. Then if you have a filament vertical, if you have linearly polarized light this direction, you expect to see a scattering peak like here and down here, really strong. But if you have a filament, say horizontal and parallel to the polarization direction, if you think about it carefully, the contrast is actually minimal. Right? So you're going to have very weak intensity horizontal direction. But if you have a combination random distribution of these two cases, you're going to have sinusoidal distribution, intensity distribution along the in this figure. Okay, so and you can also do temperature dependence. Now, once you know that the scattering pattern is from the helical pitch, you can heat the material up, and you can see that the scattering peak changes clearly as a function of temperature. And if you make plots, and then you can see that the peak actually moves. So when you heat it up, the peak shifts to small q, which means the helix is unwinding. And then when the temperature is high enough, the intensity starts to drop. So this is kind of what you expect. But what's interesting is that when you heat the material to relatively high temperature and then cool back down, you actually have a very different pitch. So the pitch is 120 nanometers versus, say, 80, 90 nanometers at the beginning. So right now, what we think is that when we make some material, we have to put the material in chloroform, and then you drop cast it on silicon nitride membrane, right? So chloroform will mostly evaporate, but very likely you'll still have a tiny bit of chloroform mixed in the material. And when you heat it, the heating actually helps drive the rest of the material, chloroform, out of the material. So when you cool back down, this is pretty much similar to the neat material. Now, to double check the theory, we can just skip the chloroform step. We just directly put this neat material on the sample holder, and we do this experiment. And you can see the pitch is 120 nanometers. So what this tells you is that, well, first is that when you put a little bit of guest material into the the NOBOW, you can actually tune the helical pitch. And the second is that the neat material, it's actually the helix is very robust. So somehow it's not very temperature dependent. So you can see that you can probe the helical pitch in one material. I mean, what's the big deal, right? So we decided to do study basically another material which is very similar but very different. So physically, so this is a twist grain boundary material. It's also a helix, but instead of a continuous helix, this is like a discrete helix. You have these symmetric blocks, and then the layer normal jumps by, say, 30 degrees or 60 degrees between the two blocks. So we have done that, and then this is also, again, as a function of temperature, you can clearly see the peak position changes. And in this case, the helix is much more temperature dependent. So you can see that the pitch changes from 100 nanometer to 200 nanometer. So, so the message is it's very simple. So we have demonstrated that with the soft X-ray technique, scattering technique, we can actually probe the helix. And in this case, this is purely a orientational variation. It's not like a density, electron density modulation. And we're hoping that this technique can also be applied to study the, say, twist bent pneumatic phase, as a lot of people have discussed today. But of course, in this case, the configuration is probably much more complicated than the simple, twisting symmetric layers. And we're also trying to extend the technique to, say, lytropic systems. So this is an example. You have also see this chiral helix formed by peptoid. So this is kind of my summary slide. So I hope I convince you that the soft X-ray scattering technique can be very useful. And again, at this stage, we have the hot X-ray, soft X-ray, and also in 6 months also we have tender X-ray scattering. So in the near future, we can do 90% of all the materials people are interested in. And this is at the end, this is a nice movie. Besides developing new techniques, we're also trying to basically speed things up, right? So for many X-ray experiments, it's repetitive. So this is just show you that if you can develop some robotic instrumentation, you can put actually 300 samples on the table, and then you can do some LabVIEW programming, like so that at 5 o'clock in the afternoon, you can put up 300 samples, and then you click go, and you come back second morning, you basically have all the data waiting for you. So this is basically it's happening. We have done some demonstration, but this is happening, and and I forgot to tell you. So the detector we have, you can collect images 300 times, or 300 images per second. So you can imagine how much data you have to handle, right? If you keep constantly, you can basically pump in data to your hard drive, and so we really need. This is basically the instrumentation part, but we have somebody working on also data, how to handle big data, because a lot of people, big data science is very hot recently. So at this point, I'll be happy to take any questions.
On the pictures you showed where you had the X-ray patterns for vertical and horizontal polarizations, can you find those?
Yeah. I think it's this one, right? Sorry, it's this one, right?
Yeah. What are these spikes that are coming out at 45-degree angles?
Oh, you mean this?
Yeah, from the
Yeah,
center.
this is so the beam comes in, shoot your sample, and most of the beam basically go through right, basically without getting scattered, right? So you need to put a beam stop to block this beam from entering in your detector, which is bad, because that's not part of the intensity. That's not the intensity you are interested in. You want to collect the scattered intensity, but not the direct beam.
Okay, so these spikes
this
are
is
maybe just diffraction around the beam stop?
Right, so the blue thing, that's basically the beam stop. And the spikes, usually you see the spikes when you have, the material has some large, say, crystalline stuff in it. So, but depending on the sample preparation, yeah, so typically you don't see the spikes, but usually when you see the spikes, that means you have large stuff which scatters strongly somehow.
Okay.
Not isotropic, not in an isotropic way.
One question. Is it possible to use a circularly polarized X-ray?
We do have the capability, and I think it's possible. I haven't explored that area yet, so I will let you know what happens.
All right. Thank you.
More questions? I have one. Do you see a chance to use this technique to examine how the nanofilaments are packed in the B4 phase?
You mean
how they are arranged together? Can you extend it past the individual nanofilament?
right? So, but yeah. So I think that basically the question is like whether. So what I told you is the contrast is from basically the twisting semantics, right? And what Peter is asking is like whether you can see it's pretty much the contrast between the nanofilaments and the air, right? So you have to have some.
What's in between?
Right. Yeah. So I believe it's possible, but you need large enough domains, I think.
I see. Is that it? Okay, let's thank our speaker.